So yes, I'm presenting to you today on electrical power systems. So background, I am from NASA Ames. I'm a contractor, just so we're clear on that. I'm technically in the Intelligent Systems division, but all my work is done in the spaceflight division. So my history is small satellite projects and small satellite avionics. I've worked on a whole host of projects ranging from 1U to 6U, and we've got a 12U coming up, followed by a 24U after that. And if you ask my boss, he'll say we have 185U. Whatever needs doing for the inside of a nanosatellite is what I do. I do the electronic design for it. I'm an electrical engineer. I graduated from University of Idaho just a couple of years ago. Main project that I work on is called the TechEdSat program out of the Nano Orbital Workshop. So our main thing is we do technology demonstration missions. We're a .x project, and we do really rapid turn technology demonstration. We're testing things like neuromorphic processors in space. We're testing new reentry systems, specifically these passive drag brake devices we call exobrakes. Let us come down well within a year so we don't become orbital debris. But the main thing is we develop 100% of our hardware in-house, everything from the structure to the EPSs, the solar arrays, all that we do in-house ourselves. To talk about EPSs, I want to have a base project to refer to. So all of you went through the ShipSat presentation, right, for systems design. So this should look pretty familiar. For reference, right, we're talking about a LEO spacecraft. It's going to be doing constant monitoring, constant observation to count these ships and these vehicles so we can start getting port traffic information. And we have a couple of mission objectives and success criteria probably coming from an initial design phase, pre-PDR, very preliminary, and we have a basic design of what the ConOps look like, especially for power systems. We're interested in, okay, we started figuring out what we want to do when we're sunlit, and we've started figuring out what we want to do when we're in the eclipse. So you have this load power table. So this is coming from maybe your systems engineer, someone who's been, doing mission design longer than you. They say, hey, we finally came out of our design phase. We have this load table. We think we know what our satellite's going to need. Can you design an EPS for us? And so that, of course, brings us to the question of what is an electrical power system? So electrical power system, I like to think of it as you have four main functions. You can think of them as subsystems, but you start saying subsystems too often and you'll never see the whole big picture. So we'll call it four main functions. Of course, we have to have something that gives us power. So we need to start with some system that gives us generation. These days, pretty much everything uses electrical power. I did have a project that was contemplating doing a mechanical computer ADCS system when they were particularly upset with MATLAB one day, but we scrapped it. So you need something to generate electrical power. When you're generating it, chances are you can't always generate enough for what you need right then, or maybe you need it when you can't generate it. So we need some way of storing power. Then we also don't always want power to flow. We don't always want the lights to be on. We don't always want your spacecraft to be completely running. So we need some way of stopping the flow. We'll call that for spacecraft inhibiting. And then it needs to get to where we want it to go. So we'll call that distribution. So our four main pieces of the ADCS are generation, storage, inhibits, and distribution. We'll come back to this a lot. So where does this fit in with some of the other spacecraft systems? I am biased being an electrical engineer and doing PDSs, but kind of objectively, the EPS is the basis of your whole system, right? If you don't have electrical power, you've got a box floating in space. Let's be honest. I mean, the mechanical engineers, you are very appreciated and you do excellent work, but we have to have electrical power to make it so we can do something. So EPS is pretty critical. Followed by that, I'd say that you have your primary controller next level up, and then you kind of go up from there to payloads, which of course the payload's probably what's paying for the whole thing. So, your priority is going to depend on your perspective. And so for EPS, we pull that out and we see our four quadrants, with generation and storage really making up the base of your little EPS subpyramid, if you will, and then your inhibits tying it to your distribution system. So to kind of give a more grounded example of what this looks like outside of a spacecraft system, of course, we'll talk about an electric vehicle. You can change the proportion of the wheels and the seat in this horribly crude diagram I threw together. This could be your electric scooter, an electric skateboard, an electric car, an electric train, whatever. We don't necessarily have generation, but we'll fudge it and say that our external power coming from a charger is our external, it's our generation, right? We have power coming into the system. We store it in our batteries. That way it's there when we're not plugged in. And then we have our distribution, which in this case is primarily going to be motor drivers, right, to get the wheels going. And then our inhibit system is kind of the key mechanism. So you can kind of think about that and, abstracting it for spacecraft is we have power coming in, storage, you've got your inhibit key system, and distribution makes it the power actually do what you need it to do. So this is what our 98 slides look like. We're going to start with a little bit of electrical theory. I'll drag you kicking and screaming back to a little bit of your electromagnetics physics 201 class. And then we'll talk about each of the subsections, generation, storage, inhibits, and all that. And then we'll start looking at, actual mission design for putting all the pieces together. Volts. Everyone is familiar with voltage, right? It's a measure of potential. General confusion I see is this is not a unit of energy or work. Volts is its own kind of thing. Your analogy for it is water pressure, right? How much force do you have behind your electric current? How big of a gap can it jump? It's kind of an equivalent to potential energy. And this is the energy of the electrons, right? We know electricity is made of electrons moving through a conductor. Volts is the potential. And of course, we have amps, current. Everyone's familiar with amps. You've got the circuit breakers in your house rated for different current values. This is the physical amount of electrons we have flowing, the volume of water. And these are tied together with resistance, right? Resistance is a physical property of what the electricity is flowing through. It's resistance to the electrical flow of the electrons, right? So higher voltage doesn't necessarily mean you have higher current, but resistance does tie the two together. And we'll talk about this a little more. We're all good on voltage and amps, right? Volts and amps. On the other side, we have watts. This is where we start getting into units of power and work. So watts is power. The big thing to keep straight is watts is an instantaneous measurement. That's my biggest peeve reading data sheets from companies and talking with systems engineers and everything is if you tell me how many watts it is, that's a snapshot. You get watts by multiplying voltage times current. Those are both instantaneous measurements. You end up with an instantaneous measurement. So when you see watts, remember, it's a snapshot. You'll usually see watts in terms of like average power rating, maximum, minimum. It doesn't really help you with power budgeting though. That's where you need watt hours. You need units of energy. So you multiply your joules per second times time. You go back to joules, you start getting energy. And that's where you actually start taking the integral and you look at power over time, you get energy. And that's where we can start doing EPS system work and things like that. And if we do a little bit of algebra, we knew that voltage is resistance times current. We flip some things around, we get that power is equal to current squared times resistance. This is important for calculating loss. P equals I squared R is something you should write down for your electrical theorem from these slides. The takeaway of that, combined with resistance, is if you're going to have high power, you usually have to have a high system voltage. That's one of the number one things I see with small spacecraft systems is these ludicrous power loads operating at too low of voltages for their system. What do I mean by that? So let's say we have a design where we have a battery that is a lower voltage than our load. This is the example for why you want your voltages to go down. So say we have something that needs 5 volts at 10 watts, and we're going to feed it from this thing that has 1 unit of internal resistance. We can supply it from either a 3 volt, right, so a lower voltage than we need, or we can supply it from a 7 volt source, a higher voltage than we need. If we start with the higher source, and we say, okay, we're going to take this higher voltage and step it down to 3 volts, we still need 10 watts, right? Conservation of energy. So if we take 10 watts and divide it by 7 volts, we know we need that much current. And if we take our P equals I squared R, we see that we lose 2 watts on the step down action to get our 7 volts to 3 volts. And if we do 2 watts and we take our efficiency, right, we get 83% efficient. On the other hand, if we want to step that up, if we take the 3 volts and step it up to 5, so instead of going down 2, we go up 2, we have a massive efficiency loss. Why? Because we need more input current. And so that is a critical thing to remember is whenever possible, try to design your system so they step voltages down, not up. Every once in a while, or you'll have one single part of your spacecraft or your system that needs a higher voltage and you just have to step it up, that's fine. But don't design a spacecraft where you have to step up every single voltage. So always try to step voltages down. You look at any consumer electronic device, they step voltages down. You look at the power grid, it steps voltages down. Across your system, as you move from generation to storage to inhibits to distribution, your voltage should be going down. Otherwise, you're just making life harder than it needs to be. Some values for when you're looking at data sheets, just seeing things out in the wild. For volts, you have millivolts, volts, and kilovolts. These days, millivolts are becoming more common to see outside of measurements. It used to be you just use millivolts for your accuracy and your decimal points after voltage measurement. Now we're starting to see modern processors running at 800, 900 millivolts. Volts is going to be the standard. Most of your spacecraft systems are going to be in the volts range. Kilovolts, you're looking at more exotic stuff. Ion thrusters typically use kilovolt levels. Physics experiments, spacecraft charging things, those usually use kilovolt levels. If you see kilovolts, you should also see someone on your team with a PhD in the title, just because kilovolts are notoriously difficult to handle in space. Here, we don't really think about it, but air is a pretty good electrical insulator. You do not have that in space. Space is a perfect propagator of electromagnetic waves, so stuff will just arc everywhere if you are not careful. So you want to have a really good design engineer on your team if you're dealing with kilovolt stuff. Current, again, you got milliamps, amps. Better not see kiloamps on your small spacecraft. If you are, talk to me and we need to patent that. Milliamps, again, becoming a lot more common to see for processing devices and things like that. And amps is kind of your whole system level. Watts, milliwatts, watts, same kind of deal. You'll see milliwatts for small individual systems, small little individual processors, and you'll see watts for larger systems, individual systems, things like that. Kilowatts is where you really start getting up there. You may see kilowatts on larger CubeSats. Instantaneous power of suddenly a pulsed load or something like that could start getting into the kilowatts range with some high-end experiments. Typically, you're not going to see that on small spacecraft. You will have watt hours, certainly. Kilowatt hours, again, is kind of large for a spacecraft. I have this example column on the side to kind of give you a sense of scale, where kilowatts, you're really looking at people rated things for anything in the kilo range, and small spacecraft are going to stay in your prefix range. And amp hours, we'll talk about watt hours and amp hours when we talk about batteries. We got to get our power from somewhere, so let's start talking about power generation. You don't necessarily have to generate power. That all just being said, if you're running a very short mission, reentry probes, one and done, some small swarm board sat stuff doesn't necessarily have generation on it. But, let's be honest, 99.9% of the time, you're going to need power generation for your mission. How you generate that power is going to be driven by what your mission is. It's going to depend on where you are, where you're going, and what you're doing, of course. But there's also the other half of that, which is what you select can also change what you're going to do. If you are driving an EV versus a gasoline vehicle, that's going to change how you drive. What are some of our options for power generation? I'm not going to read this whole thing, don't worry. But the top two here are kind of the main areas to think about. We've got, of course, good old go-to solar cells, right? We're using the photovoltaic effect to generate energy across a band gap semiconductor. Power range is basically as many solar panels as you can fit on your mission, right? You may have a tiny little area available for solar. You may have giant deployable arrays directly proportional to the area you can carry for your solar array. So it's a really flexible power generation system. You have free energy from the sun, so you don't have to pay anyone for fuel. You just stick the panels out there, you get sunlight, you get power, and they're pretty inexpensive and easy to get these days. Of course, though, they have to point at the sun. Solar panels don't work when they aren't pointed towards the sun, which you always have to remember that. I'm mentioning radioisotope thermal electric generators because this is up and coming. If you're not familiar with RTGs, which I can't blame you because they're kind of rare, you're using the heat generated from radioactive decay to produce thermal and electrical power. For CubeSats, they're starting to think about using these RHUs. These are radioisotope heating units. You get them from NASA via the Department of Energy. They're 1 watt chunks of radioactive substance that's encapsulated to produce 1 watt of heat. For actual RTGs, you can get some pretty big power densities. The Mars Science rovers, Curiosity and Perseverance, are probably the most publicly noticed examples of RTG-powered devices, just because you can't run a rover like that on solar. And some of these are pretty big. Cassini, that's going to be, almost 4.5 kilowatts of thermal power, keeping it warm, and 300 watts of electrical power. So you can get some high power densities out of RTGs, which is why I mentioned them. The downside, of course, is it is radioactive and it is plutonium. So they are incredibly hard to get your hands on because of fusion weaponry. We're not allowed to make more plutonium. There's low supply. NASA control and the Department of Energy control the supply. So you need to have a very good reason to need an RTG to be able to get an RTG. Beamed power and the other cells, beta voltaics. Beam power I mentioned because it's getting a big following now for electric aircraft. Basically, think wireless charging on steroids, where instead of having, a 5 millimeter working distance, you want to have like a 500 meter working distance, usually done in the gigahertz range of blasting something with RF radio frequency energy, and then taking that energy and converting it back into power to charge batteries. The idea being that if you have an eVTOL sitting there waiting to land, or, while it's in a city or something, you can point these directed energy beams at it to keep it charged while it's hovering or while it's nearby stuff. And beta voltaics is also a radioactive decay generation mechanism. It's much lower power. If any of you have those little tritium keychains that glow in the dark, that's basically what it is, where you use that for generation. It's kind of the easy but really low power version of an RTG. So they can be used for battery backup equivalents and things like that. Let's be honest, you're going to go with solar. So we'll talk about solar. Power is going to come from the sun. So a couple things to know is when you're looking at solar cells, you're going to see this term that's called AM, that stands for air mass. Not many companies and labs test their solar panels for space use because, the market is for terrestrial applications. So you'll see these values with your cells, depending on who you're buying them from, of AM0, 1, and 1.5. And that stands for how the equivalent air mass that they were tested with. And what that means is, the atmosphere attenuates how much solar energy hits Earth. So when you're in Leo, you're usually getting about 1,400 watts per meter squared. But when you're down here on the ground, you're getting about 1,000 watts per square meter. So that's why keeping track of these ratings is important, because if you're buying solar panels that say they're this wattage at AM 1.5, you know that you could probably expect a little more out of them in space. Versus if you're buying space rated cells that say they produce this amount of power at AM0, you know that they've already been tested at space levels of incident energy. So that's why you want to track those. We have the good old physics telling us that, our solar radiance decreases with the square of distance. So if you look at the plot here, you can start to see that pretty much use of solar past Mars really doesn't work out very well for you. This is why they're using RTGs on Cassini. All the Voyager probes have RTGs. Everything that's going at deep space needs a radioactive heat source and energy source, just because you can't fly that many solar cells way out in deep space. So where is the actual solar panel technology? This is a neat chart to keep an eye on. It's produced by NREL. NREL is your friend when doing research for power systems, especially in the research area. This is a plot of all of the major solar technologies across time. So you can see that efficiency is generally increasing. And in fact, in some of the technologies, we're starting to already reach the theoretical limits. We're not going to buy cells that cost $15 million in a research lab. That's not feasible. So where's what we can get our hands on? Most higher end missions will be somewhere up in here using triple junction silicon cells. Though, top of the line right now is about 30 to 32% efficient. If you really shell out, you can start getting into 35% efficient, but your starting price is going to be like $1,000 a watt for solar. Most research missions, university missions, most of my missions tend to be down here on single junction silicon cells. These are like what's on your roof. They're only picking up one wavelength of light. They're still pretty efficient. 22 to 26 is kind of the current right now, and they cost significantly less. So something to think about when designing solar is your efficiency is directly tied to your cost. So a couple of notes on using solar cells. They do degrade over time. This is data from some of those triple junction cells. I've actually used these before, where this column here is telling you the percentage remaining after 10 years in low Earth orbit. And you can see they're still at better than 90%. In general, if you're buying really nice space-rated cells, you can pretty much ignore degradation in LEO orbits. That being said, if you're using COTS cells, if you're buying stuff designed for terrestrial use, you're probably going to need to start thinking about degradation. Critical thing for solar is they operate on this current and voltage curve, also called an IV curve. And we know that, so this red line is what the panel will put out. So as you increase the voltage across the panel, your current falls. We get that curve. And we know if we maximize it, right, if we take power, which is voltage times current, we get this blue line. And so we're going to have this peak right here. And that's called your maximum power point. And so with solar panels, they really like having a constant voltage, constant current load to maximize them. And you do that using a special circuit called a maximum power point tracker, also called MPPT, MPP. You'll see it all over the place. That's another thing to write down, is if you're flying solar panels, you need a maximum power point tracker. You can buy them off the shelf. You can design them. It goes synonymous with solar. You want to, if you don't get it when you buy them, you will want to generate this curve on any cells you use on your mission, because that'll tell you where your maximum power point is. Although going back to the last slide, you have to be careful about this, right? Because if you test them outside, what air mass are you operating under? So you got to keep in mind that when you launch your solar cells into space, they're going to behave differently. So in general, if you estimate a 32% efficient solar array, that'll be on the high end, but that will get you there for an estimation. You don't really need to think about degradation for LEO missions most of the time, unless you're really buying cheap cells. It is important to remember that the efficiency of your solar cells does decrease with temperature. So the hotter your solar panels, the less efficient they are. Solar panel cooling is important. And the other thing to remember with them is you are getting that 1400 watts per meter squared, but you're converting some percentage of that into electrical power. So your incident energy on them is proportional to how much power you're sucking out of them. So make sure your thermal engineers are keeping track of that, because when you're sucking all the juice out of your solar panels, they'll be colder than if your batteries are charged and you're not using them. They can be tricky to manage. And the other thing to keep in mind is your conversion with MPPT is not 100%. It's usually almost 100%, 98, 97%, but you do need to think about power loss through your system. Usually, you don't just fly a single little solar cell all by its lonesome. We need to make them into panels and arrays. So how do we do that? The same is going to be true for batteries. So if this doesn't come through, it's going to be the same deal for battery packs. So we'll revisit this in a second. To increase voltage, you connect your cells in series. We've got this example here of 2-volt, 50 milliamp cells. When we stick them in series, meaning we have, say, a negative terminal up here, positive, and we go negative, positive to negative, positive to negative, so on and so forth, right? Our voltage is increasing by 2 volts after each panel. So if we have 2-volt panels and 4 of them, we get 8 volts at the end of the day. Current increases when they're in parallel. These are combining the potential, and then when you stick multiple strings in parallel, you start increasing the current. So we have 50 milliamps out of each string. We have 3 strings, we get 150 milliamps at the end of the day. So a design example. So these are the general steps you can do to start calculating some basic parameters for your solar array. So we need to start with, what does our solar array need to look like? I like to start with the power you need out of it. So say we need 20 watts, and the voltage we need out of it. So say we need 10 volts. We need to also start looking at solar cells. So we'll take some actual cell data. This is straight off of what a data sheet would give you. You can see we've got our maximum power point data provided for us there. I'll tell you that these are space-rated cells, so these are actually the AM0 values. And we'll go from there. So first, we need to figure out, okay, let's start with power. How much power do we need out of our array? And so to do this, we take our total power divided by the power we get out of each cell to give us our cell total. Remember, you can't have partial cells, so we need to round up. You don't want to round down and already start screwing yourself up, right? Always round up to the next one. So we're going to need 25 cells. Okay, and now we have this voltage requirement. How many series do we need to get up to the voltage we need? So we take our total voltage, right, 10 volts. We divide it by our maximum power point, right? We don't want to be off of our maximum power point. So we'll take our maximum power point voltage and we see that, okay, we need 4 in series. And so if we take 25 and divide by 4, as you all know, we get 7. We got to round up. We now see, okay, we've got 25 cells in 4 in series, 7 columns. So we no longer have 25, right? Because so we can then say, okay, we got these 4 in series with 7 columns. So we have a 4 series, 7 parallel array, right? Does that notation make sense? We don't want to have any partial strings. Don't design solar arrays with strings of different voltages. You'll make your EE's life a nightmare. Just keep them all the same. And we have 28 cells. We can estimate the area based on the size of the cells. And we have what's called the short circuit current and the open circuit voltage. This is if you short out the panels, how much current are you going to have? And your open circuit voltage is if you have no load on the panels, if they're just sitting there doing nothing, what's the voltage across the panels? And then, of course, maximum power points when we start loading them down, and we can estimate our maximum power. So we started trying to design a 20, but because we had to use full strings and full cells, we actually ended up with 23 watts. I'm giving you the technical background. We'll do like actual taking mission examples at the second half. I want to go through the technical EE and technology stuff first, just so you have that when we get to the mission design portion. So kind of what does an example look like of solar panels? This was an upgrade I did for a project a couple years ago. So they were using these solar panels, which use your standard single junction crystalline silicon cells. They were sitting at about 18.5% efficiency. We wanted to upgrade. So we upgraded to triple junction gallium arsenide cells. We went from 18% efficient to 31% efficient. Doing that right means that this is a 3U panel that put out a little under 4 watts. And now we can do the equivalent in 2.5U, right? So that means we can either do more power in the same area, or we can use less area and use the remainder for, imaging systems, antennas, whatever on the exterior of the spacecraft. So it's a trade-off, right? Cost versus how much power you're generating. Another system, this is another one I did. This was a 6U spacecraft. This was a 47 watt system, 2 deployable panels on here, pretty high operating voltages with a big individual MPPT converter for the whole thing. So let's talk about storage. We knew from that maximum power point that our solar panels like a constant load. And we know that if we're actually doing anything, we're probably not going to have a constant load. You don't always drive at the same speed. Your computer's not always doing the exact same thing. We're going to have dynamics. So we need something that can store energy, both so we retain our generated energy, so we have it when we don't have the sun, and we want it so we can augment the available power. If we have a 20-watt solar array and a 50-watt radio, where's our other 30 watts coming from? And just like solar, selection of what you use for storage is going to drive the mission, and vice versa. What your mission looks like is going to drive what you choose for storage. So let's look at a similar chart here for some storage options. Of course, the good old-fashioned go-to is batteries. These days, you're probably going to end up flying lithium ion, let's be honest. You have what's currently an electrochemical cell with usually a gel or a liquid electrolyte. I have more show and tell, so I'll pass them around in a couple slides here. Sealed in a metal package. For storage range, you're looking at usually about 300 watt hours per kilogram. Part of that is the packaging, right? Because if it's encased in metal, you don't have power storage there, but you have mass. So keep that in mind with power systems, is you got to think about your storage, what your pack looks like, and everything you need in that pack. Your nominal cell voltage is 3.7 volts, and you generally get about 10 amps per cell of output. Some cells will do more, some will do less. For example, the ones on Ingenuity, the Mars helicopter, were capable of extremely high output currents to run those motors. Of course, they're ubiquitous, so they're super easy to get. They're pretty safe, except they do have that nasty, explosive, burning thermal runaway you have to deal with. But they're used. I mean, they're really common. I mean, Artemis flies them, CubeSat missions fly them. I mean, they're everywhere. Under that, and slowly becoming more common in space, is supercapacitors. These are different than standard capacitors you may have used in circuit boards. If any of you have designed circuit boards or know capacitors, there is a difference with supercapacitors. They're also called EDLCs, these electric double layer capacitors. Usually they have graphene or some other nanoporous material in them, where basically it's a way to store almost static charge, if you want to think about it that way. They are very bad at long-term energy storage. They will discharge themselves pretty quickly, but they have an incredibly high output power. So they're not good for primary storage, but what they are really good at is instantaneous high power stuff like radios, things that need a lot of juice in a really short amount of time. Because batteries aren't super great at that. You can actually damage your batteries pretty badly if you pull a lot of juice out of them really quickly. Non-conventional, you got flywheels and thermal mass. These generally aren't used on small spacecraft. Sometimes you'll see really lean missions using their reaction wheels and their ADCS system as flywheels, where when they slow down the flywheels, they'll actually suck the electrical power out of them. But generally, just because you have that inertia from a spinning mass, you won't see them on CubeSats just because that would prevent you from pointing. So what you'll see sometimes in a couple of systems I've designed is you'll take your lithium ion battery and you'll charge up a supercapacitor with it, and you'll have your supercapacitor some power bus that has like a radio on it, or maybe you have an ion thruster that needs a really big jolt to get it going or something, and so that way you'll suck it out of the supercapacitor and not kill your battery. So using them together is the way to go on that. Supercaps are getting better, but you're not going to see them for primary storage. You'll see them for secondary storage, complementing a battery. Flywheels are more for base stuff. There's been some research. It's pretty hard to make it unsafe, and it also really doesn't care about the environment. They're good, in their own regard. And thermal mass is similar, especially if you have an RTG, or if you get something hot. As long as you keep it radiatively insulated in space, you don't have any air loss. So it's pretty easy to keep things hot for a long time if you can contain the radiated infrared, usually heat. So you can use that for energy storage. Again, not really practical on a CubeSat, but just something to be aware of. Battery terms to know. Number one, the C rate. Basically, it's a current that discharges your battery in 1 hour. So if you see something, especially if you're buying like off-the-shelf battery packs, it'll say like a 2C discharge rate or something like that. That means that you can discharge the pack. That's the rate to do the full discharge in an hour. So if we have a 10 amp hour pack, a 1C rate would be 10 amps. If I had a 5 amp hour pack, a 1C rate would be 5 amps, a 2C rate would be 10 amps. So when you see C in batteries, think per hour. Amp hours versus watt hours. An important distinction is amp hours is actual measure of stored electric charge. Batteries are an electrochemical reaction. They don't store power, they store electrons. Amp hours is a much better way to measure their stored charge, because watt hours will vary with how fast you drain them. The faster you drain a battery, the lower the watt hour rating is. So when you see watt hours with a battery cell, it should usually be accompanied by a discharge rate. It will say like, this is a 50 watt hour battery, and it should say at 1C or something like that. State of charge and depth of discharge are both you'll see for planning purposes. State of charge is basically your percentage full, and depth of discharge is percentage empty, if you will. So your state of charge, you can think of that as your typical fuel gauge, and depth of discharge is basically how low do you want to let that fuel gauge get before you refill. Nastiness about lithium ions, of course, they have this really non-linear relationship between the state of charge and their voltage. Older cell technologies, it was more linear. Your alkaline cells are not linear, but they're better than this, where if you're trying to figure out, by measuring voltage, what your state of charge is, you need to have pretty high voltage accuracy because of the sharpness of that curve. And you have a couple of these well-documented knees where you switch between chemical states in the battery. If they get too hot, that gel or liquid electrolyte will boil. That electrolyte boils, it produces gaseous hydrogen, and we know what happens when you take hydrogen and combine it with a heat source and or electricity. Exactly. You get boom, that boom heats up the cells around it. Those cells boil and generate hydrogen, and you get a Tesla that burns for a week. It's an issue. The other issue is that, especially in space, you don't see it quite as much, I think, on the ground, is you get what's called dendrites where the metallic lithium will slowly grow out of the cathode and short out the cell internally. You'll get that if you overcharge the cells, especially if you charge them when they're too cold. There are ways you can very carefully and systematically recharge the battery to kind of get rid of those to a certain degree, but it is something to be aware of on spacecraft, especially if you have a cold spacecraft profile. If you're running a cryo cooler or some instrument that needs to be cold and your batteries are cold, you got to be really careful with them because they will short themselves out internally, and it's a bad news. Your cell voltage has to be between 2.5 to 4.2 volts maximum. That's going to be regardless of the cell you buy. That's just property of the chemistry. They are very sensitive to being over discharged or overcharged. So you really need a battery charging circuit to keep an eye on your lithiums. Again, they also have a very sensitive temperature range where they need to be pretty warm when they're charging. When they're hot, they will keep themselves warm if you're discharging them enough. So they're a little more lenient on how cold they can be when you're discharging. But still, they have a pretty, I wouldn't say room temperature, but relatively compact range, especially for space. Lastly, if you're buying off-the-shelf battery packs, keep in mind that most batteries you buy off the shelf have a physical thermal fuse in them, so that it's usually a high temperature wax, like in fire sprinkler heads, where if the cell gets too hot, the wax will melt and break the electrical connection. So just be cognizant of that when buying cells, because you don't want to buy ones that have a really low set fuse in them. So you can sometimes buy them without the fuse. For CubeSat missions, you're probably going to end up with these 18650 cells. They look exactly like this. These are the go-to for just about everything. They make up electric vehicles. They make up pretty much all your battery packs. They're super ubiquitous at this point. JPL did a significant amount of testing and picked out these LG Chem cells, these MJ1s, as the best for spaceflight. You can look at their report, pick a different thing based on the mission you're looking for. They're tested and accepted. If you are using the cells raw, you do need to have battery protection circuits in there. A lot of projects I see don't have protection circuits, so make sure yours does. And if you're flying off of SpaceX or the ISS, batteries are going to be your #1 headache in terms of launch safety. Just like solar cells, we probably need more than one battery, so we're going to need to make them into battery packs. It's the same deal, where when we need to increase voltage, we put them in series, and when we need to increase storage and current, we put them in parallel. Depth of discharge on these depends on your mission and your risk acceptance. If you're running something that's going way out there and costs a lot of money, you may only accept 40% as a depth of discharge, right? You're never running that fuel gauge below 40%. If you're on a more aggressive mission, something that's a shorter life, more technology demonstration, higher risk, that could be all the way up to 80%, 90%, just because you aren't as reliant on those cells lasting forever. So it's something to think about when designing the mission. So let's do another design example, just like we did for solar panels. This is going to be a very similar process where we need to start with some basic information. So let's say we want a 12-volt battery pack with 40 amp hours of capacity. I'm going to pick the LG Chem cells. So these are their data sheet values. The thing with batteries is, solar panels have those IV curves. You have to keep track of. Batteries have a voltage range, right? They go from 2.5 volts when they're discharged up to 4.2 when they're fully charged. So you don't have that IV curve, but, well, you kind of do. But for these, you have a voltage range, right? Your batteries aren't always going to be at the exact same voltage all the time. So first, for these, I like to start the opposite way of saying, okay, instead of saying how many do we need for the power we need, I like to start with how many do we need for the voltage we want. So for here, right, we want 12 volts. We get, on average, 3.6 volts per cell. So 12 divided by 3.6 is going to give us 4. Then it's a question of how many parallel cells do we need? Now, this for batteries is going to depend on one of two things. One, it's going to depend on your storage capacity. And two, it's going to depend on the peak discharge current you need. And it's going to be, of course, whichever one's your biggest driving factor. So for this example, let's start with the storage capacity. We need 40 amp hours. We have 3.5 amp hours per cell. So 4 divided by 3.5 is 12. And our other thing is, okay, let's say what our peak discharge is. We want 5 amps sustained. So if we do 5 amps divided by our nominal 670 milliamps, we need 8. So in this case, our capacity is driving how many parallel cells we need, not our peak discharge rate. All right, so now that we know this, we can design the cell. So here, right, we're going to have 4 series, 12 parallel. That's going to give us 48 cells. If they're 50 grams a piece, that's going to be 2.3 kilograms of cells. We'll see our minimum voltage of 10, our maximum voltage of 16.8. So, right, keep that in mind. We wanted an average 12-volt pack, but our peak is actually going to be 16.8. And the thing with lithium is if each of these cells can spit out 10 amps, if we short out our pack, we're going to have 120 amps going through that wire. That is very important to do that math on with your battery packs, especially if you're designing your own protection circuitry, because with lithium ions, it is very easy to accidentally create these very high discharge battery packs. That's why an EV can go from 0 to 60 in 3.5 seconds, is you can get these insane discharge currents out of lithium ions, which is also why they catch on fire. So example CubeSat systems. This guy is one of our older TechEd sats. It looks like a mess, but it worked remarkably well. I think this one actually won an AIA award. This guy's got 4 of those battery packs that passed around. That gives us 30 watt hours per pack, 35 watts per pack. So if we stick 4 of them together, we get 120 watt hours of storage, which is pretty significant for a 6U, 140 watts peak output. Versus this was a backplane based design I did a couple of years ago, where these were fully custom battery packs. We did all the battery management, everything ourselves. That was only a single cell voltage. So our pack voltage was, 1 cell's worth. It was a really low voltage, but it had massive capacity on board because we weren't wasting power doing increasing voltage. It was kept at a single voltage cell. All right, let's talk about spacecraft inhibiting. So inhibits are important both from a safety perspective and for your actual mission. All right, we don't want the spacecraft operating the whole time it's in the dispenser, both because we'd launch and our batteries would be dead, and also we don't want to blast ourselves with whatever experimental radios you've got on that thing and physics payloads and who knows what else. Ideally, your spacecraft inhibits should inhibit the flow of power between all aspects of your electrical power system. They should block power from going between your panels to your storage, and it should block power from going to your storage to your loads. It protects people, especially from RF exposure, radio exposure. That's primarily the driver for inhibit systems, especially if you're launching from the space station. But it also protects all of your deployables and single-use things like that from actuating early. I'm going to keep this at the high level because it's not circuit design, but inhibits are like my #1 most complex thing to design because they can be crazy. They're also super critical to get right. Your inhibits must be approved by your launch service provider. Start early. Make sure they know what you're thinking. Make sure you know what they're thinking. Send them drafts early on, because if they do not like your inhibit system and you already built your spacecraft, you're not going to space today. In general, you need to be 2 fault tolerant for its failure, right? You should have 1 inhibit that if it fails, you have a second inhibit that's still keeping you off. So by default, your spacecraft should die if it has an inhibit failure. The protection of the launch vehicle and protection of people is more important than your mission. Talked about that it should keep everything powered off, and if you follow the UNP requirements, you should be good for just about every LSP. Most LSPs are pulling from the original nanoracks, the interface compliance document, ICD, so just about everyone has the same inhibit requirements. Some of the newer launch companies that don't do human-rated stuff are a little looser, especially if they only have other CubeSats on board, but again, talk with the provider. You're probably going to end up with a couple of inhibit types. In general, you're going to have the good old-fashioned mechanical inhibit switches on the outside of the spacecraft. You pretty much have to have these because you need a physical switch to detect when you're deployed. It's kind of hard to do that any other way. Then you may have solid-state inhibits. These would be solid-state electrical devices in the spacecraft that are controlled by those mechanical switches. So you have a solid-state switch triggered by a mechanical switch. You then may have additional enables on subsystems. So you may have separate enables for your radio. You may have separate enables for your deployables and things like that. And then you may additionally have controls at low level in software. You may have things watching for your batteries being too drained, or watching for other air states that will re-enable some of these inhibits to turn systems off. So you'll usually have something that looks like this nested system where you'll have high level inhibits and low level inhibits across the whole system. These are almost always required by the LSP, just because, again, it's kind of hard to detect if you're deployed if you don't have switches. Solid state ones are good design for power engineering. They're more efficient generally, and you can get higher power through them than mechanical switches. Having a fault tolerant system generally requires you to have subsystem switches, right? You want to have bulkhead doors on all of your systems. So if you get a leak somewhere, you can shut the door. If you don't have those doors, your whole thing's going to flood and go down. So having a segmented power system is a good idea with that. And pretty much you're always practically going to have software control over power, just because you don't always want everything running all the time. Turn it off if you don't need it. So let's look at mechanical inhibits. So these are some examples of the switch types. Most people are moving to these rail roller leaf switches, but originally was these foot switches, which you'll still see on some 1U spacecraft. It's hard to get switches that'll fit in common rails that are rated at more than 5 amps. So one of my projects is learning that the hard way. If you have more than 5 amps blowing through those, you're gonna have a bad day, which also means that if you have a really high power experiment, you can't just use mechanical switches. You need to augment them with solid state to get more power through your bus. They are simple. They have mechanical issues, right? If they can jam, you can vibrate them to death. They can eventually wear out or burn through, but they're pretty easy and straightforward to use, and they're pretty darn reliable. Foot switches, though, I would try to avoid those if you can use the roller switches. Foot switches have a tendency to jam. There's been more projects that have had issues with those foot switches versus the roller leaves are pretty tolerant. For solid state inhibits, you start getting more complicated for electrical design. You really need to have someone designing your solid state inhibits. Generally, what you'll do is you'll have power coming in, you'll have your first redundancy and your second, right? So if this one fails, you're still turned off by this one. And you'll have the signals to control these switches come from your mechanical switches. So your mechanical switch will close and send a little bit of current through it, and that will close this big giant MOSFET up here that can handle a couple hundred amps or whatever you need for your mission. You'll do the same thing coming from your batteries. Some LSPs tell you to inhibit on the ground. I tell people to be careful with that because you can get what's known as ground float, where just through static charging and things, the ground of your batteries can become different from the ground of your spacecraft. And when you connect them back together, you get a discharge. So in general, you want to keep all your grounds connected. If you do have to do ground inhibiting, I would use a mechanical switch just because it's a lot easier than trying to do it electric. You do get increased power handling and you get better efficiency. They're lower resistance than mechanical switches, but you do have the complexity of design and you can get some weird things going on with especially ground inhibiting. Subsystem enables. This is really kind of depending on if you're designing your own system or if you're buying stuff off the shelf. In general, making it so you can turn bits and pieces of your spacecraft on and off is a good idea. That way, if something fails, you can isolate it from the stuff that's still working. If you want to save power, you can turn off power to things you aren't using. You're enhancing your fault response and your power conservation. It does increase your electrical complexity, but generally it's worth it. It is important to think about what level of control you want to have early, especially when you go into software, because sometimes if you try, say we've got a radio here and we have it turned off and our primary computer doesn't realize we've turned it off because the power control is on some local controller that hasn't told the primary computer, hey, I turned off the radio. Are you going to enter an error state where your primary computer says, hey, I'm trying to talk to the radio and the radio is not responding? And is that going to screw everything up? Or even worse, is it going to try talking to the radio and the radio is going to be damaged because it's not powered, but you're sending signals to it? So it's things to think about when you're designing at this level. And finally, software and or analog circuitry enables. So for example, the ShipSat safe mode mechanic here. Implementing the safe mode, is this a piece of software that's sitting here watching your battery voltage, or is this an actual analog circuit watching your battery voltage? And if your battery voltage goes too low, how are you controlling your other systems, right? Are you physically turning off power to them, or are you commanding them to enter a low power state? And if you do that, how is your larger system going to respond? And that's where you start getting into system engineering mixed with electrical engineering of, again, how do I make sure that all of my computers know what's turned on or off, especially if I have that happening at a hardware level and not at a software level? So it's something to think about during design. This is an inhibit system that's flown probably more than a dozen times off the ISS. And this is about as simple as you can get for inhibit systems. We've got our batteries connected by 3 rail switches and a remove before flight switch to our primary computer and power distribution system. Their solar panels hooked up to it. And so what happens is we come out of the dispenser, we have our switches close, our computer boots up, and we have a timer that starts counting down, usually 15 to 30 minutes, depending on who we're deployed from. The software commands another enable to start turning on radios after that inhibit timer has gone. So that'd be kind of like HAZOPs, where we're in this kind of low power waiting to get far enough away from the launch vehicle before we can turn on radio state. How many fault tolerant is this? Technically 4. Technically, if we got enough solar power, we could boot the system because there's no inhibits between the solar array and the power board. We got around this by saying, well, let's look at our risk scenarios. Our risk scenario is we're integrating this indoors under this sort of light and our RBF pops out. These lights do not put out enough power to turn on our spacecraft. What's the other use case? Well, they accidentally pop it out of the deployer on the space station or something. Again, not enough incident light to actually trigger the thing to turn on. Sometimes you can get by with this, especially if you have smaller solar arrays, but again, it's a risk you have to evaluate. More complex system. This is a mix of solid state inhibits that are controlled by rail switches. This is more complicated than I would generally want to do. This was on that big 6U I showed with the deployable arrays, where similarly we had a ground inhibit on the solar. So solar voltage comes in, it's ground disconnected with a switch there. We overrode the switch because we were having issues with the switches, and we convinced the LSP that we didn't need ground inhibiting. We've got our 2 redundants on our batteries down here coming into charge, and we have 2 redundants on the discharge path. So we're inhibiting solar on the ground, we're inhibiting solar before it gets to the batteries, and we're inhibiting the batteries from from powering the rest of the spacecraft. And there's a ground inhibit on the batteries. This was way too many inhibits for the spacecraft, and each individual battery cell had all these inhibits on it. So while it was 8 fault tolerant on the inhibiting side and like 32 fault tolerant in terms of surviving an inhibit failure, it was way too complicated. I have to have a closed circuit for power to flow, which means I got to have my positive and my negatives connected. And I've got 2 switches on both. So if I lose inhibit 2, I've still got 3-1 in my RBF, and vice versa. If I have the RBF in, it's 4. If I pull the RBF and that's closed, then I've still got 3 inhibits, all of which have to close for my system to turn on. So this is what's generating the timer from deployment, because these switches are mechanical. They close as soon as we pop out. This then gets powered as soon as we pop out. It starts counting down a 15-minute timer, and then we can turn on our loads and things like that. This is a pretty standard way to do it with mechanical switches and then a timer. Usually have a time requirement from ISS and SpaceX deployments, because they don't want your radios screwing with their ground comms. So they want you to be far away before you kick on your comms. Again, though, if you're using these mechanical switches, you're limited to usually on the order of 5 amps for your entire system, just because you're passing all of your power through these switches, and these tend to be pretty small switches. So it's something to keep in mind. For distribution, the solar panel, maximum power points, and our batteries having voltages that are all over the place, we probably need something to regulate our voltage and power to all these devices. Things are going to require different voltages. Our batteries can output this extremely high power that we need to protect against. So we need a power distribution system, or a PDS is usually what it's called. It should produce regulated voltages we need. It should monitor them. And it can be a single module or a distributed system across different subsystems. It really depends on if you're buying something off the shelf or designing it yourself. In general, though, you're pretty much always going to have to do some amount of modification, just because everyone's spacecraft is different, and it's really hard to design a universal power system for each of them. It's like if everyone's house had the same number of outlets in the same place. It would work for some people, it wouldn't work for others. So PDSs look different. It depends on the mission. These are some one project developed where the PDS is integrated with their primary computer and their primary radio. It's supposed to be an all-in-one board sort of deal. Great for smaller, really integrated missions, but not great for high power stuff, just because you're limited by area and space and everything else you're trying to do there. Versus having a more discrete system with a dedicated power distribution system set in here. Generally, what you need for power distribution requirement generation, you'll have kind of a table of these values you'll need. This is going to come from actually starting to select hardware. PDS is one of the last things you'll design just because you pretty much have to have everything it needs to power already figured out. So what are some of these values you need to keep an eye on? Minimum input voltage is critical. It's also sometimes called your under voltage lockout, UVLO. This is where if you dip below that voltage, you're going to get errant data. The computer, the processor, whatever it is, just can't run itself. You can even get errant data, or especially critical, you can go to write things to memory and you won't have the memory, you won't have the power available to actually write them into memory. So you'll think you wrote it, but you didn't. Maximum input voltage, you exceed that, you're probably going to damage something. That can also be called over voltage lockout, OVLO. Maximum sustained power, that's usually used for things that have, again, pulsed power. So you won't always see a rating like that unless it's a radio or something that's got a kind of steady state behavior with transients during its operation. And so they'll tell you what the peak of those transients are. So for example, our ADCS unit here, say it's 10 watts nominal, and then, maybe when it's changing what it's pointing at, it's drawing 15 watts versus radio, very low power while it's just sitting there listening, but then a huge power pulse when we send a radio burst. Inrush current is also important to look at, especially for in your inhibit system, because when you turn things on and connect them to power, there's usually an initial power surge as those internal electronics charge up for the first time. Some devices will have internal limiting, others will not have internal limiting. So you want to pay attention to that on data sheets to tell you whether or not you need to expect this possible pulse and you need to limit it, and if it can be limited, or if it will do it itself. And there's some easy ways to. Tracking communication protocol isn't usually part of the PDS unless you're doing a really integrated power system, but it is something to keep an eye on as you're designing your bus. For example, I'm going to call these requirements. This is more of how do you start kind of thinking about a power distribution system. You would come up with a table of the voltages and currents you need for your various devices. You would come up with your battery pack, your solar capacity, what your inhibits look like, and things like that, and then compare that with what's available to you. PDS is something where most projects will either do COTS. It's getting a little more common to try to do custom power distribution systems, especially for university projects. Say we've got these two options that we can buy off the shelf. It's always a question of, how can I make them meet what I need? And so it's usually, for this one, we need this bus at 5 amps, but this only gives us a bus at 2.5 amps. We only need one, and this has 4, so we can tie some of these together to increase output current. We can tie these voltages together to get the currents we need because we have more outputs than we need, but we need higher current, and these can do. Keeping an eye on what their solar capacity is like, having single maximum power point tracking for your entire solar system versus having multiple power point tracking, maybe one power point tracker per string of an array. It's all things to think about when you start doing PDS, and it's really just kind of a trade study and quantitative analysis. If you're looking at COT stuff, is what do you value most and what's going to best meet your requirements? And the fact that nothing usually ever exactly meets what you need off the shelf drives a lot of people to custom. And so in general, keeping your power distribution simple makes your life simple. Again, always try to lower a voltage when you can. And these are some things that's been designed to augment pre-existing power distribution systems. So like this one, the power distribution system had 4 solar panel inputs. We were going to have 5 panels. This takes 5 panels and converts it to 4 panel outputs that the converter could handle. And it also makes it so we can turn off solar generation, which we needed for that mission. And like this one takes one giant power input from the battery and splits it out to a bunch of channels with current protection on it. So doing Frankenstein patchwork EPS systems is pretty common, especially for research stuff, because nothing's ever going to exactly meet your needs off the shelf. Let's do a mission design. Your EPS, as we talked about at the very beginning, really supports the rest of the mission. Generally, your mission design needs to be pretty well underway before it's worth talking about an EPS, right? If you're just saying, okay, we're going to build a CubeSat, and you start with, okay, we're going to fly a battery pack. It's like, why? Right? It's what are you actually trying to do, right? We're trying to, image ships and vehicles at ports. Okay, now we're getting somewhere why we actually need a battery pack. ShipSat, the design example, they designed the power system dead last. That's kind of honestly the way to do it. That being said, even at the beginning stages, the reason I went over all that technical stuff first is you want to have a good background knowledge so you keep your mission design reasonable. Example here is don't build a 3U CubeSat going to Neptune that's got terrible solar arrays on it and some giant load on it, right? You got to keep in mind what the reality of physics and the current state of the art is. I'm not really going to talk about requirements writing and things like that because that's a lot more systems engineering. The great thing about being on technology demonstration missions, you're probably going to have to deal with them, and you'll also help generate them at some point just from producing numbers. I put these slides together from a back and forth I did with Ames's mission design department, kind of a CubeSat Mars probe based experiment. And so what you'll see is there's a lot of back and forth as you go through the design mission of what is driving what. Your mission design is going to be a recursive process, and this sort of recursion is going to be true for every single subsystem of your spacecraft, your ADCS, your comms, your EPS, where you're going to start with some concept. You're going to have that concept drive your high-level requirements, and then you're going to pass to the engineers who are going to start looking at the instruments you have to have, the subsystem those instruments are going to require, and then the actual numbers, right? Are we actually able to fly enough batteries and solar to run this massive black hole telescope thing you want to fly? Can we actually run this 5,000 watt radio to talk to something we want to run to Pluto or whatever? And then, of course, you've got swap and cost considerations. Can we physically fit this on the launch opportunity we have? Do we actually have the money to do this? That is a huge thing, especially with a research project, is do we have the money? Do you have the time? Do you have the launch opportunity? Needless to say, spreadsheets are your friend. Maybe your first one is back of a napkin calculation, but throw everything into Excel as soon as possible so you can update numbers as things change. Excel sheets among mission designers and grant writers are just as guarded as the Coca-Cola recipe. For EPS design, you're kind of going to have your requirements in two categories. You're going to have your generation and storage requirements versus more of your distribution and inhibit requirements. Generation and storage are going to really come from mission design, your launch service provider, and things like that. These are more of your less technical, if you will, requirements of like, okay, what are your operations driving? What's your power budget looking like? How is pointing in your ADCS going to influence your solar arrays and things like that? And just your general spacecraft design, right? This is all stuff you can start ironing out before you know the actual part numbers of what's going inside the spacecraft. Versus then distribution and inhibiting. This is, okay, I really can't start doing distribution system design until I know what it needs to distribute to. I need part numbers at that point. We need to pretty much have con ops and our operations done. And LSP requirements also, right? Do we have a fixed launch provider at this point? We started off saying we're going to launch a 6U. Do we actually have a ride for it now? And what are the requirements of that ride? So generally you'll start with these and then start getting into your actual double E details, if you will. Breaking down the steps, and this is what we're about to go through. So step one, generate a load table. This is where you start with your subsystem estimates and you start looking at your per orbit operations. What are the estimates for each of the subsystems I need? Do I have an ADCS system? Do I have a radio system? Do I have some instrument that requires power? What are my estimates? Are they just random guesses, or am I actually at the point where I have numbers? And then for per orbit operations, it's okay, what am I doing while I'm in the sun? What am I doing while I'm in the dark? Start getting more qualitatively. What are you trying to do with this? We know our load table and we know operations. We can start putting those two together into our power budget. Balancing that power budget yields what our generation and storage needs to look like. And that's where we then can go to an EPS system. So we're going from mission design and kind of our building blocks to actually looking at energy balance. And then after that, finally, we can do actual distribution, right? And we go from what we need to power, how we're going to power it, how we're going to get the power there. So generally, you'll stay at this phase for a pretty long time while you iron out what's actually inside of the spacecraft and how it's going to operate. And then you'll move here. And as you do this, you'll refine the load table. You'll go back and forth between the two as you look at your battery options and solar options. And then when these two are hammered out, you'll start looking at your power distributions. Let's do a power budget. So again, unless you're doing a really short duration mission, you need to stay power positive, right? If you're going to go out for a week with your phone and you don't bring a power bank or a charger with you, your phone's going to die. That's fine if you're going home at the end of the day, but if you're out and you still need your phone to work, you didn't balance your power budget properly. Power in's got to equal power out. It used to be for a really long time that you were in a period of sunlight and then a period of eclipse. With all of the spacecraft swarms going into more traditional LEO orbits, a lot of CubeSats are getting more opportunities to do sun synchronous orbits. It's something to keep an eye on because, as the name suggests, you don't have an eclipse usually in sun synchronous orbits because you're following the same inclination of the sun. You're going around the Earth in time with the sun. The downside of that is you may be launched not at high noon, so you may not have full sunlight during your sun synchronous orbit. So that's a very important thing to know for mission design. If you're doing a sun synchronous orbit, is it's called an LTAN. It's a time of day basic equivalent. So if you have like a midnight LTAN, you're always going to be in the dark, versus if you have like a 9 or 10 a.m. LTAN, it will always be 9 or 10 a.m. sunlight for your CubeSat. I would actually say that ChipSat should be launched in a sun synchronous orbit at like noon or something. So that way you always have noonday light over the thing you're trying to image. It's pretty typical for Earth or imaging satellites to be in some sort of sun synchronous orbit. So they always have the same sunlight, the same shadowing and things on what they're trying to image. I will put the asterisks here. So this is going to be an engineer's perspective of how to do this. Mission designers will give you a different perspective. It's a back and forth, and you're not going to be the only person on your team, otherwise it wouldn't be a team. So different people's perspectives, everyone's got a different background on how to do design like this. I'm the one providing the electrons at the end of the day, so I like to take that approach. Other people keep it just at times and energy. This is one way to do it. Other people will probably show you other ways. This is the load table from ShipSat. So say we've done the first round of napkin calculations. We pulled a couple of estimates from some other projects your university did. We have some numbers. We know we're going to have a power system, obviously. We're going to have a radio, an ADCS, a CNDH. We've got heaters to keep ourselves warm because we know our batteries will die if they get too cold and we try to charge them. We have our actual payload imager and we have a GPS, so we know where a satellite is. I'm going to start putting numbers on here because I got this from system engineers. I know these are estimates and they're probably pretty good estimates, but I just want to make sure we've got, I'm going to start thinking about actual radios and power and stuff. So what am I going to do? I'm going to come in and I'm going to say, okay, for this mission, it's an orbital imaging mission. I probably need a lot more downlink for images than I need uplink capability, right? Because what would I be sending to the spacecraft besides commands? So I'm going to switch in an orbital network radio. I'm going to use an Iridium modem. So that way I have constant 24/7 uplink command to my spacecraft. I don't need a ground station. I'm then going to say, okay, we're going to have a dedicated transmit only radio for our actual image data. It's going to be S-band, higher data rate. It will need a ground station. So we'll do a ground station pass to dump our images. I'm going to say we're going to downlink during the eclipse because I want to utilize all of my sunlit time for imaging. Right? Why am I going to spend my precious moments of sunlight where I can actually see ships and cars pointing at a ground station? Ground stations don't care if it's day or night. They run 24/7. And finally, I'm going to say, I want to compress the data even further, maybe even do some processing on board. Let's add, current state-of-the-art processor in this thing. So we can try to do maybe some AI machine learning algorithm on board to autonomously recognize what's a boat versus what's a car, right? If it's on something that looks like water and it's a blob, it's a boat. And if it's on something that looks like asphalt and it's a blob, it's a car, something like that. So then I'll go in and I'll pull some random reasonable actual hardware estimates so I can start getting better values. So, we'll use an Iridium SBD modem. We'll use the S-band. We'll use an off-the-shelf AAC 1U ADCS unit. We'll use a 4K camera link imager. We'll use a Novatel GPS, and we'll use an NVIDIA Jetson Orin for our primary processors. I'm pulling in some estimates. This may not be what you end up using, but just to give yourself some actual hardware. You can get hardware estimates. I'll talk about sources at the very end. Background research and looking at similar projects is your absolute friend. That is critical if you're flying weird stuff, is to find other weird people that have flown weird stuff and talk to them, because they will save you so much time and hassle if you can get their lessons learned before you have to learn them yourself. So we got all those values. We made those equipment estimates. So I'm going to make a new load table here. I'm going to assume, again, that we're going to point and transmit to one ground station when we're in the eclipse. I'm going to say we really only need the heaters when we're in the eclipse, because otherwise we're going to be blasted by the sun. And we probably also don't need to do a ton of processing while we're in the eclipse, because at that point we'll just be packaging data up for transmission. So we're going to be working really hard computationally when we're doing all that pointing and imaging, and we're going to be pretty much just waiting for the ground station to line up when they're in the dark. What I've done here is we have an equipment list. With each one, we have an associated operational power. Again, remember, power is instantaneous. So you can think of this as like the average value it's going to take. We have an operating voltage, which I pretty much just have there to track. I made everything 5 and 12 just for making things easy. And then I'm splitting the orbit into, when we're sunlit, I'm calling that imaging mode. And when we're in the dark, that's ecliptic. And so for our core bus, right, our electrical power system always needs to be running. It's going to be on 100% of the time. If that isn't 100%, we're going to have a bad day. When we're transmitting, we're not transmitting during the day, we're not downlinking, and at night we don't have a duty cycle, right? Duty cycle is percentage of the time you're on. I'm estimating ground passes. So doing a duty cycle for ground passes isn't the way to go. I'll show you what I do on the next slide. For receiving, right, we want that radio to always be on, so we're always ready to receive some uplink command, especially since we now have global coverage. So that's going to be 100% day and night. ADCSs can take a lot of power when they're slewing your spacecraft around versus when they're just station keeping. When you're pointed at something, it's pretty low power, but when you're suddenly changing what you're pointing at, you can draw a lot of power. I'm breaking the ADCS up into 2 sections, and I'm saying that, okay, during the day, we're probably pointing at stuff like 75% of the time, because we've got this whole list of coastline areas we want to image. We're going to be busy during that daylight period. At night, we're only pointing at 1 ground station. Maybe we'll do 2, but either way, it's going to be less pointing than during the day. So I'm going to keep that ratio. Primary computer, right? I said we're going to be busy processing during the day. We're not going to be doing much at night. And for the imager, right, the imager, we aren't actually going to be taking that many pictures, right? We're going to be doing a lot of stuff in preparation to take that picture, but taking the picture is just, click, done. So we don't actually need that much power for our imager, and it's not going to be running at night. GPS, we want the GPS always to be on, because if we lose GPS lock, it's going to take us a while to find it, and we may not know where the satellite is without talking to our Air Force buddies to get the TLE. So we want to have that GPS running all the time. And for heaters, right, we really probably don't need heaters during the day, but we're going to need them at night. So now it's time to do math. I'm going to estimate a 100-minute orbital period. That's kind of like a 415, 420 kilometer orbit, just so that gives me runtime. That may or may not be what this actually flies to. That's why using Excel is important. So if you just have a cell that says orbital period, you can update that as needed. So for this example, I'm going to say 100 minutes. And I'm going to say that our eclipse period is the same as daylight period. So I've got 50 and 50. I'm then going to estimate for our ground station pass about a 12-minute pass. So it's kind of an average. It's a longer side for an average. That's why I don't have a percentage for ground station pass, because just saying 12 minutes, right, I can either just remind myself it's 12 minutes, or I can do the math to figure out what percentage of 50 is 12. And then I got to update that if I change my orbital period. So some things you will want to track immediately in actual time increments. It's just easier than trying to figure out a duty cycle. I can take now my duty cycle and my time per orbit and come up with time. Does it make sense how I got this? All right, this is step 1. This is where I'm taking my 12, right? I'm saying I know it's just going to be 12 minutes, so it's just 12 minutes. Now that I know duration and I know power, I can calculate energy, right? Because I now have power times time. I'm going to maintain what I need in the imaging period versus what I need in the eclipse. I'm taking the power, multiplying it by the time, and I'm getting these columns. And I'm adding up these two to get my per orbit totals. I have not done calculus since graduating. Everything is addition, subtraction, multiplication, and division. What does this tell me? If I add up these columns, I can see that I need 51.3 watt hours during imaging. That's the sum of my imaging energy. If I sum eclipse, I need 33 watt hours, which means over the total orbit, I need 84.2 watt hours. If I have 84.2 over a 100-minute orbit, I know my average power is 50.5 by dividing, right, watts per hour divided by a little over an hour. What does this mean in English? Well, I need to enter the eclipse with 33 watt hours of stored energy, right? Because I'm not going to have any generation. So I need to enter with 33 watt hours in my tank, which means when I'm in the sun, I need to generate that 33 watt hours plus the 51.3 I need while actually in the sun. While I'm in the sun, I need to generate 84.2 watt hours if we want to maintain constant operations. Let's turn this into an EPS. So I have the numbers I just came up with. I've got our sunlit load in watt hours. I've got our eclipse load. I have the total generation we need while we're in the sun, and I have the time we need, or the time we have in the sun. These are all just basically from starting a ConOps, right? So first thing I'm going to do is I'm going to say, okay, how much solar power do I need? I'm going to determine that by saying the watts I need divided by the time, right? Because watts times hours divided by hours gets me back to watts. So I need 101 watts of solar generation to produce 84.2 watt hours in 50 minutes. Logically makes sense because I have less than an hour to do it in, so this number should be bigger than that number. Then I'm going to say, okay, let's start estimating solar panels. If I have a 30% efficient panel as just a baseline to use for estimating, I have watts solar times 1 over my efficiency. So if I have 30% efficiency, I need 337 watts of incident energy. Now I can do area, right? I'm in space. I'm at AM0. I can estimate 1400 watts per square meter. So I can take this, divided by 1400 watts, and I get that I need about 0.241 square meters of area. So let's convert that to square U, right? I have a 10 by 10 centimeter per U, so that gives me 24 U of solar area. Jumping now to energy storage. I need 33 watt hours of energy storage. I'm just carrying that number, 100% of my eclipse load. I'm going to estimate 10 watt hours for 18650 cell. Again, be careful using watt hours for cell estimation, but for now, this is our preliminary run through. I'm going to use watt hours. That means 33 divided by 10 is 4. And so if I multiply that by 50 grams, I'm going to estimate I have 200 grams of batteries I need. First run through of going from ConOps values to actually starting to get solar panel areas and battery pack sizing. Make yourself an Excel spreadsheet, save it somewhere, use it on all your missions. Don't redo your work. It's going to be the same math for everything. 24 U of solar panels sounds like a lot, especially on a 12 U spacecraft. Is this going to fit? If we look at the proposed spacecraft, right, because now I'm starting to go back to mission design. If I just came up with these numbers, do I need to start looking at changing ConOps? Well, if I look at this, I've got these 6U panels, and I've got 4 of them. 6 times 4 is 24. So I think we're there. And in fact, yes, if we just make it so this last panel also deploys, so they all point towards the sun, we're good to go. So far, I'm seeing a thumbs up on my initial round of ConOps. I know I'm working with good mission designers who've done this before, and that we're starting with a good base point. However, I have absolutely no margin on this thing. I am assuming that all of my solar panels will work at 100% of their rated power. I'm assuming they'll be pointed fully at the sun, and I'm assuming they're going to work perfectly forever. I'm also assuming that I am going to completely discharge my batteries every single eclipse, which how many times do you completely run your car out of gas before going to the gas station? Maybe once. You do this to your batteries, you're not going to have batteries anymore. You're going to have hunks of lithium. So you don't want to do that. So let's start adding margins and see what this looks like. So what I've done is I've done the same math. I've added in, now we have our solar generation margin. I'm saying I want 20% margin on my solar generation values. So what does that do? You can see that that number propagates through and it kicks us up from needing a 24 U array to a 29 U array by adding that 20% margin. For batteries, I'm saying let's only do a 40% depth of discharge, right? We're only ever going to get down to 40% of our tank. That's pretty conservative, especially for a small sat, but I am saying that this is an imaging mission. Important people seem to want to look at this data, so I'm going to assume they're going to have a conservative risk posture. So let's say 40%. I'm also going to have 20% margin on top of that. Not only am I letting the fuel tank only get down to 40%, but I'm going to carry 20% more capacity than I need. So as those battery cells age, I have margin. That suddenly kicks us up from needing 4 cells to 10 cells, and I go from 200 grams to half a kilo of batteries. Margins suddenly are making this look very different. So now we have to start asking the hard questions of, I've only got 28U of panels. Are we going to buy more expensive panels to make it so we have better than 30% efficiency, or can we accept less margin? If we start doing things like safe mode, we lose pointing capability. Are these acceptable risks, right? Because now all of my solar panels are facing the same direction. We start tumbling, I'm going to lose generation. I've got 10 battery cells. That's almost 2U of volume. Is that physically going to fit in our 6U spacecraft with our instrument? Again, back to risk posture. Again, all of our solar panels are facing the same direction. Is that a risk we can handle? If we deploy tumbling, if we can't generate power for the first 2 or 3 orbits because we're detumbling, is that battery pack estimate enough to make it so we could detumble without dying? That's where the iterative process comes through, and working with people who are very well experienced in mission design can help out with that. You get back into this recursive thing of maybe additional things come up, right? Our 12U launch slot turns into a 6U launch slot. We just don't have the budget for deployable panels. They're expensive and they're hard to make yourself. Maybe we can't do that. You can't get your NTIA license for S-band because you didn't file it 2 years in advance. So you're stuck with VHF, much lower frequency. Your 3U imager, they do testing on it and they realize we need a better lens on this, and the lens is going to take up another U. Maybe we do the math and we find we're in a sun synchronous orbit and now we're running hot and we don't need batteries, we need radiators. You're going to go back through your power budget. It's an iterative process. You got to be prepared for that. And that's where having spreadsheets are your friend, and being flexible is your friend. Keeping everyone up to date on system changes is critical, so everyone can track changes and adjust risk posture. And you have the question of, what's driving what? Is your EPS going to be driving the science you're doing, or is the science you're doing driving your mission opportunity? Do you have, for universities, and even most of mine, it's, we have a 6U launch slot. We're going to do whatever we can with that 6U launch slot, even if it means we're not imaging every day. We're imaging once a week or twice a week, just because, that's the only generation we can fit. We can only have a power budget that supports once per week imaging instead of everyday imaging. So let's take these estimates. Let's say we passed, and we're now going to turn it into an EPS design. So I had the draft power budget done, right? I saw an estimate of how many solar panels I need. I have an estimate of how many batteries I need. So let's actually turn these into what the actual solar arrays look like and what the battery packs are going to look like. With all of this, you're going to have constraints of power budget and your mission design versus your opportunity scheduling costs. So let's pull in our equipment list. So that way we have powers and voltages, and let's pull in the values we just came up with for battery sizing and everything. So I'm going to start with battery pack design. So the battery is really the backbone of the whole thing. We're primarily going to be drawing power from our batteries. So let's start with batteries. So most of our systems need 12 volts to operate. Remembering the most important thing, right? I don't want to step up a voltage, so I want a battery pack of at least 12 volts. If I have these combinations of cells, right? If I have one cell, it's going to be about 3.6 volts. I have 2, it's going to be about 7.2 volts, so on and so forth. What configuration should I pick for this spacecraft? This is where looking at your risk posture and your mission is important. I'm going to say it should be 5S because all your solar panels are facing the same direction. If that 12-volt ADCS system turns off, I'm not going to have solar anymore. So I want that ADCS system running till the bitter end. So I want to have a battery pack that has a low dead battery voltage of 12 volts. And if I have to, I can run that thing dead and my ADCS will keep running. So I'm going to go with 5S for this mission. Same slide as before, but this time we're going to pull in the values we just got. So this is how we got these values. I got 18-volt pack, and I know I need at least 10 cells from our initial estimate. I'm going to use these cells. So I'm going to start with the series we need. If we do the math again, 18 volts over 3.6, we get 5 series. We get 5 series validation from saying 12 volts is our minimum. We could fudge it and say 4 if we didn't have that 12-volt critical system, but in this case, I'm going to stick with 5. For parallel cells needed, I've got 99 watt hours I need, and I've got 10 watt hours per cell. So I've got 10 total cells, right? So if I've got 5 in series and I need 10 total, I need 2 parallel strings. So this is what my battery pack is going to look like for ShipSat. I've got a 5S 2P pack, 5 series, 2 parallel. It's going to have a peak discharge of 20 amps. I've got a voltage range of 12.5 to 21, and I've got a nominal storage capacity. Since I've actually designed the battery pack, I now have amp hours of capacity. This is going to be a lot more accurate than my watt hours, and I can use that going forward as we do more detailed design of the EPS system. So I've got my battery details. I know charge storage, so we can start looking at the solar array. The important thing for the solar array is, again, I don't want to step up my solar array voltage. So my solar array needs to be at least as high of a voltage as my battery pack is when it's fully charged, which in this case is 21 volts. We started with 12. Now when we're fully charged, we're at 21. So I need a solar array that's at least 21 volts at its maximum power point. So let's do the same thing with solar array design. So I said we need 121 watts for my power budgeting, and I need at least 21 volts, and I'm going to use these triple junction cells. I'm going to assume we've got some money to spend on this thing. How many cells do I need? I need 148 cells. If I am buying $3,000 cells, that's going to be a lot of money. How many do I need in series? If I've got a 24 volt target here, I picked 24 because 24 sounded good. Anything above 21 is fine. 24 gives me a little bit of margin. I'm going to need 9 in series, which means I need 16 columns. So what is this going to look like? I'm going to have a 9S 16 parallel array, 148 cells. That's going to take up 30 U of space. How did I suddenly wind up at 30 U? Because I needed a higher voltage and I needed to make full columns of cells. So all of a sudden my margins are growing and I'm now at 30 U. And not only am I at 30 U, but I'm only at 118 watts and I was shooting for 121 because of those column estimates. So I am suddenly starting to run into trouble with my solar array. We don't have 30 U, right? We said at best case, we've got like 28. So how am I going to cut this down? Well, if I get rid of one of these strings, I go from 16P to 15P, that helps. I'm down to 28 U. However, I'm also down to 111 watts. So this is the question of what's important, margin versus making the mission. My minimum to meet the power budget is 101. We're making 111. So we're still power positive. We just don't have 20% margin anymore. We have 9% margin. Is that enough? Is that going to satisfy our risk posture? Are our mission designers happy with that? Those are the questions you have to ask. And why this iterative design is important is you very easily end up just by following the math here of, we can't carry 20% margin on this mission with 30% cells. We either got to buy really, really expensive cells to get to like 35, 40% efficiency, or we need to reduce margin. And if we reduce margin, is that acceptable? To kind of summarize what we just did, we designed a battery for ShipSat. It's going to be 5S, 2 parallel, 100 watt hour pack. It will fit into 2U, right? This is what I'm presenting to my mission design team after they told me to go design them a PDS. I'm telling them, here's your battery pack, here's your solar array. It meets the minimum you need, but it does not meet the margin you told me to meet, right? What do you want to do about that? And so again, you get back to this recursive design. What am I changing? Do I need to change my ConOps and the mission concept as a whole? Do I need to go to a 24U spacecraft instead of a 12 to make it so I can carry that capacity? Or am I fine down with the reduced capacity? Can I buy more efficient cells? Do we even have the money for 30%? Maybe we only have the money for 20% efficient cells and I'm even worse off than I thought I was. Or can we start changing ConOps? Do we actually need to run this thing 24/7, or can we charge up over a couple of orbits and then run operations for a little while? Right? Either you got to design an EPS to make it so everything works, or you got to start managing your ConOps to make it so the EPS you can fit works. So for drafting your PDS requirements, again, PDS is like the absolute dead last thing you do. So this is going to be super high level. Generally, just what does your battery pack look like? What does your solar array look like? We just designed those. What is your nominal system powers? If I add all these up, if everything's on at once, I have 98 watts of load, which is generally how power distribution systems are specified as their maximum power handling. So, I just need to basically create a table that will let me come up with EPS requirements. So this is what it could look like, is here's what we have from our load table and what we just designed. I've got a bunch of 5 volt and 12 volt loads. I've got this lithium ion battery. I've got this solar array. I need standard inhibits and standard switching to turn everything on and off. Say I've got these two options. Which do I pick? It's going to be what is your best solution? What most closely matches what you need? What can you augment? What can you customize? Maybe you decide both of these aren't going to work for you and you're going to have to sit down and design something custom. This is where you'd start, just coming up with a list of what it needs to do so you can start generating requirements from that and start doing trade analyses. And so for planning paths, this is generally what I see. So your first question is, are you going to go with COTS or custom? All right, are you going to buy it or make it? And from there, it's the question of, okay, are you fully buying your bus? Are you building your whole thing from scratch? Or are you doing a mix? Most university projects do a mix. And then from there, you've got your second level of, okay, if we're doing COTS, is everything coming from the same place, or are we picking and choosing bits and pieces? If we're doing it custom, are we building it in traditional modules, or are we doing some super highly integrated thing? If you're mixing it, right, for this presentation, are you buying the EPS or are you making the EPS? And stepping through more design choices here, ultimately what you kind of get at is your typical university, research is you buy an EPS. And if you buy an EPS, the best thing you can do is just design your systems to match that EPS. Otherwise, if you're doing a custom EPS, the reverse is true. Design your EPS to match your COTS modules. Saving that till later stages of the design really helps you not be miserable. And if you're doing full COTS, I would recommend just buying it all from the same place. I was on a project for a year that did trade studies, basically, of trying to see if there were enough COTS modules out there to build a whole spacecraft. Granted, this was in 2021, and the answer at that time was no. It may have changed now, but trying to come up with interconnects for different companies' stuff was going to be a nightmare. If you've got money to burn and you need something that's easy, just buy it all from the same place would be my recommendation. We'll end with validation and testing real quick. This was from the emission design course, the Dandy. Let's say this thing's a sphere covered with solar panels. It's a 43 kilogram nanosatellite. We design it so it's got 120 watts of solar panels on it with 40% margin. What are your thoughts? I'm presenting this at PDR and I say, if I cover this in 120 watts of solar cells with 40% margin, I will be power positive. And you say to me, I'm conservative. This is going to be in the lower thermosphere. It's going to get particles and gunk on it. So I'm carrying a large margin. That's fine. It cannot all be exposed at once. How many suns are in the sky? One. And how many sides of this sphere are going to be sunlit? Half. So if I have 40% margin, is that going to cover me if only half are lit? No. Multiple sun theorem is a downfall of a lot of projects during PDR because it is real easy to forget that there is one sun. Technically, yes, you'll get some reflection off the Earth and maybe you'll get a little bit of power generation on the other side, but you got to remember there's one sun in the sky. It's only going to hit one side of your spacecraft at once. All right, let's look at this. This is the mass budget for ShipSat. I'm presenting this to you at PDR. What do you say to me? I've got 25% of contingency across the board. I've got masses for my power system, my solar arrays, all my payloads and bits and pieces. I've got a 1.5 kilogram imager and a 1.1 kilogram ADCS. What are you telling me if I show you this at PDR? No batteries, right? We just did the battery design and we said we need 2 kilos of batteries. I don't see 2 kilos of batteries anywhere. Forgetting a pretty critical part of your power system and your mass budget and not having contingency to cover it. So that's also part of why you keep contingency in. It's generally that you'll have pretty high contingency at the beginning of your design and work it down slowly as you remember things you forgot at the beginning. These are two things I see at PDRs, is multiple sun theory and forgetting pieces of your power system. For validation and testing, it's conservation here of your actual drivers of risk acceptance, schedule, and cost versus assurance and validation. You're always going to want to test 100% of everything, but feasibly, you usually can't do that. What are the most critical things to test? EPSs, they're one of the few things that touch every single piece of your spacecraft, right? Because everything needs power. They're notorious for having edge cases, right? When your batteries are really low or really high, or while they're even changing, weird things can come up. And because they talk to every system and power every system, that's where your weird interconnected issues start showing up when you have EPS. testing is always a balance of how thorough you're going to be versus what you actually have time and resources to do. One thing you can do is modeling. This is demonstrated in the ShipSat example. So this would be using Excel or some other calculation tool to start generating rough plots of just power in versus power out in different modes. You can use if and else statements in Excel and come up with equations to add things together during operational modes. You can start generating plots like this. The best thing you can also do is get hardware in early and start doing hardware in the loop testing. If you're buying COTS parts, some companies will give you access to a piece of hardware they have sitting on a bench somewhere that you can remote into and start testing with. What we'll do is you'll start with the power budget. You'll get pretty far along in design. You'll basically have everything designed with margin, and you'll start actually doing your hardware testing, and you'll get test results. That's where you'll start actually getting current, right? You'll start being able to measure amp hours. You'll start being able to measure current flow, and you'll feed that back in to your power budget and refine it and see that, okay, yes, we are good. We carried enough margin that with the actual spacecraft and testing, we're good to go. Or you'll see that, okay, we don't have quite enough margin. We need to, once every month, we need to not do ops so we can top off our battery or something because that value was just a little different than we thought. I will call out powered TVAC testing, putting it in a vacuum chamber, pumping it down, and running it is really important. When you're testing it on the ground, on the bench, the biggest thing you have in terms of electronics is you have convective cooling, you have air. When you don't have that convective cooling, all your stuff's going to run hotter, and as it gets hotter, it gets less efficient. Doing powered TVAC testing really helps you see issues, and it lets you know if everything's going to work the way you think it is. I push for powered TVAC testing now. I used to not, but I do now, because just putting it in a TVAC chamber and seeing if it works afterwards really isn't good enough if you really want good system validation. I'll kind of wrap here with some of the critical questions to answer during your testing, which for solar arrays, if we take the spacecraft outdoors for testing, which is pretty common, are you going to be power positive? The answer may be yes, it may be no. It depends on that margin and also where you're testing. If you're testing in Seattle versus here, if you're testing on a cloudy day versus a sunny day, don't freak out if you're not power positive during outdoor testing. Always remember what you designed for. And your failure modes. If something happens to an individual cell or one of your panels doesn't deploy, what does that do to your mission? Battery testing. This is a big one, especially from the Artemis launch. If your launch is delayed and your spacecraft sits in a dispenser for months, what's going to happen to it? If you deploy with dead batteries, can you recover? If you deploy with 10% charged batteries, can you recover? What happens to your power system when it's really low? If you've got software running on there looking for under voltage stuff, is that going to interfere with some ConOps thing and create some weird software state because you didn't test it to see what would happen if it deployed with low power? You always started it from the same state in your testing. Edge cases are really important to test for batteries. And of course, for cell failure, if one cell fails, what happens to your pack? Thinking about that. For regulations on your load, what happens if your whole spacecraft boots at its coldest temperature? If the thing deploys in an eclipse, if your spacecraft is, -10, -20 C and the batteries are dead, how's it going to behave? And then how's that going to change as it warms and charges up? What happens if one of your active subsystems is accidentally turned off? Either it's turned off by some power protection feature, some battery protection feature, you accidentally command it to turn off. Are you going to put your whole spacecraft into an air state, or is it going to be able to recognize, hey, this is turned off, and correct it, or tell you this is turned off, you need to fix this before this command can be executed? And for inhibits, if you got mechanical inhibits and they vibrate a whole bunch, how's the spacecraft going to respond? Right? Generally, microcontrollers and computers in general do not like it when you sit there and spam the power button on and off, especially if you're doing it at like 300 hertz, right? So you can really easily screw up memory if you're sitting there booting 300 times a second. So what happens if your inhibits start vibrating? And also, if one of your inhibits has a latent failure, right? Let's say you're doing the easy route of putting all your current through your inhibit switches. You keep having that pulsed radio load, and those inhibits keep getting hotter and hotter and hotter because you never cool off, and one of your switches melts. What's going to happen? All right, is your mission going to end, or do you have something in place to route over that switch after you've been deployed? You can do all the simulation and testing you want, but at the end of the day, the real world is pretty complex, which is why we run these missions in the first place. This is about 2 years of data from a 3U. These waves here are the eclipse and day cycles. And these longer ones are experiments we've run. This particular mission was flying a 3.5 teraflop GPU with a neuromorphic processor connected to it, which drew a lot of power when we ran it. So this was a mission where we accepted at the beginning, we said, everything's working and we can achieve minimum success if we run this experiment once. So we're going to run it once, and we're going to really run it once. And then after that, everything else was gravy. And it was, okay, let's keep turning this thing on and off and see how long it lasts. This is incredibly difficult to model. And this is also something where our operations are driven by our power budget. We're waiting till we're charged up before running this thing, and we're running this thing until we can't run it anymore. We don't have a time constraint on it. Our power system will drive what our operations look like. So I just talked to you for 90 slides. So where do you even start? Fire hose, right? Start with the critical subsystems you need. What are the key pieces of equipment you need to achieve your goals? Do you need an ADCS system is one of the first questions to ask. Do you need pointing? And then after that, it's what kind of a radio do I need? What kind of a processor do I need? What are the core components? Don't get down, below like 6 things. Keep it basic. Start looking at estimates. Okay, I need an ADCS system. Let's start estimating what the power for that's going to look like. Great resources are the NASA CubeSat 101 handbook, the NASA state-of-the-art small spacecraft technical report. You can also look at, I like to collect trade magazines and white papers from various companies. Even if I never buy it or actually fly it, I at least have a reference for some system that's analogous to what I'm looking at. Sign up for trade magazines, go to trade shows, and just collect documentation. So you kind of have a library of how to estimate this stuff, because you got to start somewhere. Once you have those estimates, put it into a table, right? Get a list of what your equipment is, put together the power and the voltages they need. And from that, you can start doing a very rough first draft power budget. And from that first draft power budget, you can start estimating the solar area and the battery pack you need. And right off the bat, you can probably look at it and say, this will fit in a 6U, or this won't. This could fit in, we're thinking a 6U, but we can actually fit this in a 3U. That first iteration, maybe you don't even have margin on it. You're just get it done, see if you're in the ballpark. And then you can start asking yourself from that, right? Is this looking like it needs to be driven by the mission, or is this going to be driven by the available space we have for solar and batteries? Can we follow our ConOps, or do we need to follow our power system? Then you start the iterative process of, okay, now, let's go back to our mission goals and our ConOps. Do they need to change? What are our limitations and restrictions here? You're going to iterate through it again, right? You go through it the first time and you see, okay, we actually have more space for solar and batteries than I thought. We're flying a mostly empty 6U, it turns out. So, okay, what can we pack? Do we want to remove generation capacity and just fly what we need and be lean? Or do we want to throw more stuff in here because we have the space and we have the power, or vice versa? You just got to start somewhere, and starting with an educated guess is the best place to start. And if you have a design that actually feasibly closes, congratulations, you've got farther than 50% of projects get during their first design phase. Of having something that actually closes is excellent. So that's what I've got for you.